Chapter 5 is about rational expressions. And what those are, and if you take a look, you can see a few of them down here. They kind of look like fractions, except that instead of having one number divided by another number, you've got one polynomial divided by another polynomial. So it's just a quotient of two polynomials, one divided by another. So something like what's there, those three examples. And I guess that 4, I can point that out. Technically, that is a polynomial, right? It's a polynomial of degree 0. So you can have things like that, and they will show up. And I know it says this section is about multiplying and dividing, and we're going to get there. But the first thing is about how to get the domain of a rational expression, because this is a new concept that we haven't had. With polynomials, you can sub in any real number you want for the variable, and you'll be able to simplify it. You want to sub in an integer, a fraction, a radical, everything's going to work. Why is there going to be a problem now? Because it's possible to divide by 0. There might be a value that you could sub in for the variable that would result in division by 0, and that value would have to be left out of the domain. So that's basically what we've got to work with here. So like it says here in these 2 bullet points, what you want to do is basically just figure out what numbers lead to division by 0 and leave those out. So it says that the domain is everything except for the numbers that if you subbed in would give you division by 0. So basically what you do is you just figure out what numbers lead to a 0 in the denominator, and then you say, okay, the domain, it's everything except for these. So what we actually do, instead of finding the domain, it's more like you find the restrictions, and then the complement of that would be your domain. So in order to get the restrictions, what you would do is you set the denominator equal to 0 and solve. Because then that'll give you the values that would make the denominator 0, and then you just make sure you leave those out. So like for number 1, where we have 6 over x minus 4, you would set the denominator equal to 0 to find the restrictions, or in this case restriction, there's only going to be one. But to get the restrictions, what we're going to do is we would set x minus 4 equal to 0, and solving that's not too bad. You just add 4 to both sides and you get that x equals 4. So that's our one restriction, so the domain should be everything except for that, because the 4 causes trouble. It gives you a 0 on the bottom, and you don't want that because then you get an undefined expression. But nothing else would give you a 0 on the bottom. So you just have to make sure you leave out that 4. So the domain, if you're going to write it in set notation, which I think it's how the book wants it, so therefore that's how the homework would want it as well, it would look something like this. So the set of all x such that x is not equal to 4. So that vertical line after the first x, so there's the left bracket, then the x, and then that vertical line basically translates to the phrase such that, if you were going to say it out loud. And so it would be all x such that x is not equal to 4. So everything except for 4. I suppose you could write it in interval notation as well, although this chapter seems to focus more on set notation. But I mean, I guess it would be negative infinity to 4 with a parenthesis around the 4, union 4 to infinity with a parenthesis around the 4 again, right? Everything except for 4. You could do it with intervals if you wanted, but we're going to stick to the set notation since that's what the book's got and that's what the homework's got in this section. Next one, number 2, basically you do the same thing that we did in number 1, except that the denominator is a little bit more complicated. But it is one that we can factor, so that's nice. So in order to find the restrictions, we're going to set the denominator equal to 0. So we're going to set a squared minus 5a minus 6 equal to 0. And that will factor because x minus 6 times x plus 1 will multiply out correctly, right? We need a pair of factors of negative 6 that add to negative 5. So that's what's going to work. And then 0 product property, right? This is a thing that we just had very recently. So we can set x minus 6 equals 0 and x plus 1 equals 0. So either x is 6 or x is negative 1. Those are going to be our 2 restrictions. So everything except for that. Oh, and I switched variables, didn't I? I changed from an a to an x. Let me fix that. Those should all be A's. I don't know what I was thinking about there. I think I messed it up and then just kept going since I then kind of became reflexive. But yeah, let me make that actually look right. So A equals 6 and A equals -1. Sorry about that. Usually it's X. I think I just kind of reflexively started doing it there. But we can't have A be 6 and we can't have A be -1 because those numbers would give us a 0 in the denominator. So the domain should be everything else. So it'll be the set of all A such that A is not equal to 6 and A is not equal to -1. Right? Everything else is fine, but those two numbers are going to cause trouble. Throw them out. Okay, number 3. Looks like we would do the same thing. So in order to get our restrictions, we would set the denominator equal to 0. So we're going to set x squared plus 25 equal to 0. However, in this chapter, there are no imaginary numbers. And I mean, I guess that makes sense because you think, well, when we jumped ahead, they were in chapter 7, but we hadn't really talked about them before. So it makes sense that they wouldn't be in chapter 5 yet. And they actually don't show up until chapter 6. There are a couple of reasons why with rational functions you don't really deal with imaginary numbers where you just stick to real numbers. The biggest one is one of the things that you'll end up doing with rational functions. And this will be more of a 151 thing than an 091 thing, but you end up graphing them. And how do you graph complex numbers? Like if you had an ordered pair, and let's say your y coordinate was 4 plus 3i, how do you plot that exactly? Right? Like that concept doesn't even really compute, right? So that's one of the reasons, but we're just going to stick with real numbers for now. And that's the biggest, right? Like how do you graph imaginary numbers, right? We don't really have that idea. If you end up taking a class in complex analysis, there is actually a way to do it, but we're not going to get into that right now. So what's going to happen here? Well, the thing that's on the left can't be less than 25 because no matter what real number you sub in for x, if you square 0, you get 0. If you square anything else, you get a positive. So the smallest that expression could be on the left would be 25. So there's no way you could get it down to 0. So that thing that I have that bracket around can't be less than 25. And that would mean that there are no restrictions. All right, so what does that mean as far as like what's your domain going to look like? It depends on if you write it in set notation or not. So the easiest way to think about it is that it's just everything. So it's just all real numbers. Or if you prefer it written with the bold R, so usually when you write it by hand, if you write out the bold R for real numbers, it just has like a double stem, which I don't think our homework's going to use that notation, but if you look up this sort of thing online or something, you might see it. So I figured it was worth throwing in. Or if you want to write it in set notation, it looks sort of redundant in set notation because you're not putting any constraints on it. It looks like you're saying the same thing twice. But it would just be the set of all x such that x is a real number. And that does feel a little bit weird in set notation because it looks like you're saying the set of all real numbers that are real numbers. So it's like you're just kind of going around in a circle. But if you were going to write it in set notation, that's what it would look like. And I think the way the homework is set up is that it gives you like the 2-option multiple choice questions for these, where if it's one where there are no restrictions, you just pick the option that says all real numbers. And then if you have one or more restrictions on the domain, you pick the other option and then you write it in set notation. I think that's the way that the homework goes. All right, I think that's pretty much it for the domain for now. You just really have to worry about division by 0. So you just check for what values would result in that, you leave those out, and you should be good to go. All right, the next thing is simplifying rational expressions. All right, well, this is kind of like simplifying a fraction. So I'm just going to write one in up here. So let's say if what you had to do was you had to reduce 30 over 70. So if you had to do that, it's going to be 3/7, right? Which I think for a lot of people that ends up being kind of reflexive almost because they both end in 0. You go, oh, they're divisible by 10. Yeah, they are, right? So you could write 30 as 3 times 10, and you could write 70 as 7 times 10, and then you could divide out or cancel out those 10s, and you'd have 3/7. Yeah, sure. So that's basically what you do even when it's not just a number, not just an integer in the numerator and the denominator. So if you do have variables or if you have binomials, you try to find things that you can cancel out. Another thing with the 30 over 70 is that when you rewrite it, so like how I have it as 3 times 10 over 7 times 10, if you're trying to reduce it, that's the one you're going to pick, right? Because you can cancel things. What you would not pick, if I write it way over to the side here, a thing that you wouldn't pick, I don't know, maybe 3 times 10 over 5 times 14. Right? You probably wouldn't pick that one. You would eventually end up in the right place because you could cancel the 5 with the 10 because 5 goes into 10 twice, but you can cancel that 2 with the 14 because 2 goes into 14 7 times, and you'd get there, but you wouldn't do it like that, right? You would kind of gear it toward where you could cancel stuff immediately. And that sort of thought process actually really helps here. It's the same kind of mentality, even though it's a polynomial in the numerator and in the denominator rather than just an integer. So that's what you try to do, is just find what you can cancel out. One of the big things though, and this actually doesn't have a huge effect on the homework in this section, but it does in the future, that when you cancel stuff, if there are restrictions, they don't go away. So like it says there, x squared plus 7x minus 8 over x plus 1, that will reduce to x plus 8 because x squared plus 7x minus 8, if you factor that, it's going to be x plus 8 times x minus 1, which would then be over x minus 1. And then you've got the x minus 1 written as part of a product in the numerator, so you could cancel these, and you could say, oh, well, then that's x plus 8. But you still have that restriction. So the restriction doesn't go away even if you cancel out the part of the denominator that the restriction comes from. When you graph these, which, like I said a few minutes ago, that's more of a 151 thing than an 091 thing. But when you graph these and you get that kind of cancellation, that gives you kind of an unusual thing going on in the graph, actually. Like you get this open circle that just suddenly shows up. So it does have an effect that those restrictions don't really go away. But I'm actually going to write in the domains for numbers 4, 5, and 6 on this page, just to kind of really stress that point, that when you cancel out a part of the denominator with a restriction in it, that restriction's still there. So with 4, we've got a couple of polynomials there, which I think the first thing to do is just see what you can factor. See what you can factor, then see what you can cancel, and then, I mean, that's pretty much it. So for y squared plus 12y plus 32, that'll factor into y plus 8 times y plus 4. And then in the denominator, that's going to factor into y minus 9 times y plus 8. And we can cancel stuff. So I'm going to leave it. I'm going to leave that one alone, and then I'm just going to recopy it with the cancellation, just so like the steps are a little bit clearer. You wouldn't have to rewrite this, I wouldn't think, if you were doing one of these on your own. But just for illustrative reasons, I'm going to do it like this. And then I'm going to cancel things. So light green for canceling. Y plus 8, y plus 8. Right? We can cancel them because both of those y plus 8s are parts of products. Right? So it's all multiplication and division, between the division line and all the parentheses. So we can do that. And then what we're going to end up with, it looks like, is y plus 4 over y minus 9. And it looks like that's our answer. And it is. But then the domain, if we had to write out what the domain is, it would be the set of all y such that y is not equal to 9 and y is not equal to negative 8. So basically for me, I'm getting the domain from that one before there's any cancellation. Because even though like at the end in the final answer it looks like the only restriction is 9, that one that we canceled out, that would still be a restriction on the domain. So we'd have to leave out the negative 8. All right, number 5. Let's see, we've got a sum of cubes on top and a difference of squares on the bottom. Because you could rewrite 5 and you could say, well, that top is x cubed plus 2 cubed. And then the bottom is x squared minus 2 squared. So then for a sum of cubes, that'll be x plus 2 times x squared minus 2x plus 4. Right? The binomial has got a plus because there's a plus in the original expression. So that means there's a minus on the second term here. And then the 4 is just the 2 squared, right? So it's first term squared minus first term times second term. But I rewrote it as 2x instead of x times 2. And then the 2 squared at the end. And then on the bottom, that's a difference of squares. So we can write that as x plus 2 times x minus 2. And it looks like we're going to get some cancellation in here. Right? So I'll just rewrite it real quick. And then I'll have one that I can draw on. So x squared minus 2x plus 4 over x plus 2 times x minus 2. And just looking at that, you can't factor the x squared minus 2x plus 4 any further. It would be impossible to get a middle term that close to 0. But we can cancel out those x plus 2's. So it looks like what we're going to end up with is, I think I got enough room over here, x squared minus 2x plus 4 over x minus 2. And there we go. There's our answer. And then the domain, it would be the set of all x such that x is not equal to 2, but also x is not equal to negative 2. Right? So the negative 2 is the one that got canceled out because that comes from the x plus 2. But again, even though we canceled it out, it's still a domain restriction. All right, number 6. All right, with something like number 6, specifically its denominator, when those sorts of things show up, I would rewrite that in standard form first. To me, that feels like it's easier. I guess if you can see what to do without doing that, then you can do it that way too. But I would rewrite those terms in the opposite order, just so it's in standard form. So I'm just going to rewrite this. I'm going to leave the numerator alone of 3n squared minus 20n minus 7. And then on the bottom, that's going to be minus 2n plus 14 if I write it in standard form. Then the numerator does factor, so we need a 3n and an n to get the 3n squared. And then, let's see, it's a minus 7 and a plus 1 to get the minus 20. And then on the bottom, remember that when you have a leading coefficient that's negative, you got to factor the negative out. So negative 2 gets factored out, and then that'll be multiplied by n minus 7, since negative 2 times negative 7 will give you the positive 14. And then from here, I'm just going to rewrite this real quick so I have one that I can write on top of. We are going to be able to cancel, right? You can see it right away. It's the n minus 7. And that's exactly what's going to happen. So back to the light green, since apparently that means cancellation. We can cancel those out, and then what we're going to end up with is, I guess I kind of need to go into the next line here, it'll be 3n plus 1 over negative 2. Or if you just want to bring the negative out front, which is a little more customary, the negation of 3n plus 1 over 2. Like that. And then the domain, I suppose this one, if you're not careful, if you just look at the final answer, it would look like the domain is all real numbers, but we have to make sure we exclude the 7, even though it got canceled. So the domain would be the set of all n such that n is not equal to 7. All right. There is a common mistake to watch out for when simplifying things. It would be to do something like this. Like if you had x plus 4 over x, to then say, well, we're going to cancel out the x and that x, and then we're going to say that that's 4. Oh, I changed colors. There. So then this one here, this is a no. The reason that doesn't work is because in order to cancel things, it's got to be part of a product. The x in the denominator is, because I guess you could view that as basically being x times 1, right? And you can say, all right, yeah, that's part of a product. But the x on top isn't, right? It's part of a sum. And that's why you can't cancel it. And then just for another example of this effect, what if you had something like x squared plus 2x plus 5 over x squared plus 3x plus 5? The thing that you don't want to do here would be to say, oh, we've got things that look the same. We've got 5s and we've got x squareds. And then to say that this is going to be 2x over 3x, or 2/3. So this is another no. So there's the red, no. All right, so again, the x squareds and the 5s, they're getting canceled. They're parts of sums, not products, and that's why it doesn't work. And this is one of those things where if you've done a lot of this, then this is a thing that you probably don't really think of. But if you're kind of new to it, it's a kind of a step that everybody takes at some point, right? Even though it's not the thing that you want to do, it's one of those things where at some point everyone does it. And the book actually had a great idea here. And what the book said was, if you aren't sure if you can cancel something or not, just sub in, like, do the cancellation, like what you think the cancellation is, and sub in on both sides and see if you get the same thing. Because if you get something different, then it doesn't work, right? So what the book says to do is, so if you aren't sure what you can cancel, sub in a value and see if you get the same thing on both sides. So, like on, I guess the one that's on the left, that'll be easier. What if we sub in a 2? Then you'd have 2 plus 4 over 2, which is going to end up being 3, right? Because this is 6 over 2. So this is 3. It's not 4, right? So that kind of thing. Maybe sub in a couple of values rather than just one, because there's a chance that you could get lucky, right? Like the one that you pick might be one where it happens to actually work out. So maybe 2 of them would be better than 1 of them, just on the off chance that you get lucky on the first one. But yeah, I mean, I think that would be a good thing if you're unsure. Just if you go, all right, I think it's this. But then if you sub in and it's not working out, then that's not a legal move. But generally, you can cancel things if they're parts of products. But if they're parts of sums or differences, you can't. All right, the next thing is multiplying two rational expressions together. Okay, so the name of the game here pretty much is try to make the overall expression as simple as you can. And the way that you do that is by canceling everything that you can cancel out. So dividing out or canceling out, I suppose saying divide out is a little more proper, but I think most people think about it as canceling out. So factor everything. Then when you multiply two fractions, like if you had to multiply, I don't know, 7/9 by 2/5, if you had to do that, then you'd say, well, it's 14/45, right? Because when you multiply two fractions, you multiply the numerators together and you multiply the denominators together. Same thing. Even though it's more complicated, it's not just integers, you got polynomials in the numerators and denominators, you still do that. If you're multiplying two rational expressions, you multiply the two numerators, you multiply the two denominators. So basically what you do is you factor everything that you can factor, then you can combine it into one giant rational expression by multiplying the numerators and multiplying the denominators, cancel out whatever you can cancel out, and you should be good to go from there. All right, so number 7, that rational expression on the left doesn't have anything that we can factor, right? The x squared and the x minus 5, they kind of just are what they are. So I guess I can just rewrite them. However, the one on the right has some stuff that we can do. So x squared minus x minus 20, we can factor that, because then that'll be x minus 5 times x plus 4. And then on the bottom, there's a common factor of x. So if we factor that out, we're going to be left with x times x plus 4. And okay, well then we've got everything factored, so now we can multiply the numerators, multiply the denominators. We'll have one giant rational expression of x squared times x minus 5 times x plus 4 all over x minus 5 times x plus 4. And then let's see what we can do. So we've got a couple of x minus 5s. We got one on top, one on the bottom. We can cancel them out. We've got a couple of x plus 4s. I would probably just stop here, even though we're not actually done, and say we're going to have x squared over x. But remember how there was that exponent rule where you can subtract the exponents when you have the same base and you're dividing? We can just do that. Or you could view it as that we're going to cancel the x in the bottom with one of the x's on top. Like if you think of the top, that x squared is x times x, then you could cancel the one on the bottom with one of the ones on the top, right? You'll end up in the same spot. Either way, this is just going to be x. So that's the answer. Look at that, right? The problem at the beginning looked far more complicated than the answer that we ended up with at the end. And these have a tendency to work out like that. We're actually going to see it again in number 8 and I think also in number 9, where they look really complex, but they're really not that bad. Number 8, I kind of messed up, so that second numerator should be r squared minus 13r plus 30. I changed one part and then I forgot to change the corresponding part. But the first thing I would notice with something like this is that first denominator is not in standard form. So I would fix that first, I think, and then just kind of go from there. So I guess I have a lot of rewriting to do other than fixing that up. So I would rewrite that as negative 3r plus 9. So it's in standard form with the degree 1 term before the degree 0 term. And then times r squared minus 13r plus 30 over r squared minus 4r minus 60. All right, and then see what we can factor. R plus 6, we can't do anything, right? It's degree 1 with no common factor, so it just is what it is. But then in the denominator, we could factor out a negative 3. We have negative 3 times r minus 3. Since negative 3 times negative 3 would give us that plus 9 back. And then next numerator, r minus 10 times r minus 3. And then in the denominator, we're going to have r minus 10 times r plus 6. And if you're looking at this whole thing all together, it looks like a ridiculous number of things are going to cancel, and that's kind of the idea here, because we're going to get a very nice answer. But if I actually do the multiplication, and we get one giant rational expression, its numerator would be r plus 6 times r minus 10 times r minus 3. And then the denominator is going to be negative 3 times r minus 3 times r minus 10 times r plus 6. And yeah, we're going to cancel a ton of stuff because we've got r plus 6's in the numerator and denominator. We've got r minus 3's. We've got r minus 10's. Okay. And once you've canceled everything out in either a numerator or a denominator, since it's happening to us right now, what we're left with in the numerator is 1. And then in the denominator, we've got a negative 3. So 1 over negative 3, or more conventionally to write it with the negative out front, you get negative 1/3, and that is the answer. So another one that simplifies way, way down, and so does number 9, actually. Number 9 looks a little different because it's got two variables in it, because it's got a's and b's, but other than that, we're still kind of playing the same game. So let's see. That first numerator, we'd need a 3a and an a to get the 3a squared. But then we have to get a b squared, but with a negative middle term. So like the coefficients there, to get a plus b squared, they've either both got to be 1 or they both got to be negative 1. And since we're getting a negative middle term, they both got to be negative 1. So minus b, like so. And then that first denominator looks like it has a common factor of 5. So if I get that out, and then I'd be left with 3a minus b times, let's see, second numerator looks like a common factor of 6b. So 6b factored out, we'd be left with a plus b. And then on the bottom, that's a difference of squares. So it would factor into a plus b times a minus b. All right, once again, you can turn this into one gigantic rational expression, multiplying the numerators together and multiplying the denominators together. So 3a minus b times a minus b times 6b times a plus b. And that's going to be over 5 times 3a minus b times a plus b times a minus b. And once again, all kinds of cancellation is going to happen. So let's see, 3a minus b, 3a minus b, a minus b, a minus b, a plus b, a plus b. All right, almost everything once again. And it looks like all we've got left is a 6b on the top and a 5 on the bottom. And that's it, right? Can't do anything else with that, since 6 and 5 don't have any common factors. All right, so not too bad, right? I mean, it's basically like simplifying, except that you have more stuff, right? I mean, since the way you multiply is just you multiply the numerators together, you multiply the denominators together, it's like simplifying a rational expression, except that you have two of them. Or you have one gigantic one, I guess, when you multiply the numerators and denominators together. But it's not too different. Dividing has one little step that we haven't had yet, which is essentially, in that first point, the multiplying by the reciprocal. So pretty much that's how you do it. And then it turns into multiplication. Just like when you divide by a fraction, you would multiply by the reciprocal, right? Like if you were going to, I don't know, let's say if you were going to divide... So 3/11 divided by, I don't know, 1/4, then that would be the same thing as 3/11 times 4/1. So you'd get 12/11. And that's pretty much what you do, except that they're variables. But it's that same concept. So this first one, I'm going to write that as 3x squared over 4y times 16y cubed over 15x to the fifth. And then we're multiplying, and we're going to play the game that we were just playing, where you try to cancel everything that you can cancel. Here, because there are no binomial terms or anything, right, there's no like x plus 3 or x minus 8 or anything like that. It might be easier to see what to do if you kind of rearrange it all, like to have the integers first and then the x's and then the y's. So that's what I'm going to do. Like I'm going to write this as one giant rational expression, but I'm going to rearrange the order, which you can do if you're multiplying, right? Any order you want. So 4 times 15 times x to the fifth times y. All right, and then we can see what we can cancel. Well, let's see, 4 goes into 16 4 times, and then 3 goes into 15 5 times. So what we're going to end up with now is 4x squared y cubed over 5x to the fifth y. I suppose you could use the those exponent laws here and say, well, then this will be 4/5 times x to the negative 3, because you get the exponent from 2 minus 5, and then times y squared. But then you'd want to rewrite this with a positive exponent, and I think the most common way to write this would be 4y squared over 5x cubed. Right, you got to bring the x down so you get it with a positive exponent. But I think that's how most people would write it. And instead of using the exponent rules, if you want to view it as cancellation, like you're canceling that y in the denominator with one of the 3 y's that are multiplied together in the numerator, you can do it that way too. You'll end up in the same place. But the main thing is when you're dividing by a rational expression, it's much simpler just to multiply by its reciprocal. Right, that'll get you to the same place, and that's much easier to deal with. All right, so the next thing, number 11, I think the answers aren't quite as clean as they were in like 7, 8, and 9 with some of these. I think you end up with more stuff left at the end, but we'll see. So first things first, I'm going to rewrite this as multiplication by the reciprocal. So 5a plus 30 over 7a squared minus 35a times a squared minus 3a minus 10 over a squared minus 2a minus 8. All right, factor whatever we can factor. First numerator has got a common factor of 5. We'll get that out. So we'll have 5 times a plus 6. First denominator, I'm getting ahead of myself. First denominator, looks like we would factor out a 7a, right? 7 and 35, like both of those are divisible by 7, but then there's at least an a in each term. So we can factor out a 7a, and we'd be left with a minus 5. And then let's see, second numerator, that would be a minus 5 times a plus 2. And then in the second denominator, that's a minus 4 times a plus 2. Okay. And I think at this point, you would think, all right, I'm going to cancel whatever I can cancel, right? And that's what we're going to do. So let's see. We can cancel the a minus 5 there with that a minus 5. And we can cancel the a plus 2's. And it looks like that's it. So it looks like what we're going to end up with here for an answer is going to be 5 times a plus 6 over 7a times a minus 4. And that is it. So yeah, that one doesn't work out quite as clean as like 7, 8, and 9 did, at least as far as the final answer goes. All right, then number 12, a similar kind of idea, although if you look at what's going on in 12, we've got, if you look at the two numerators anyway, we've got trinomials where the leading coefficient's not 1, so maybe the factoring would be a little more challenging here. I guess we'll find out. First things first, rearrange that so it's multiplication by the reciprocal. All right. So 9x squared minus 19x plus 2 over 8x plus 72. And that's going to be multiplied by x squared plus 16x plus 63 over 3x squared minus x minus 10. And then it becomes factor whatever you can factor. All right, so then in the first numerator, let's see. Well, we know what the constants have to be, because in order to get a 2, it's either 2 and 1 or negative 2 with negative 1. If you're in a negative middle term, it's negative 2 and negative 1. However, there are different options for the leading terms, like you'd have a 3x and a 3x, or a 9x and an x. It's going to have to be a 9x and an x, because we need to get that middle term to be pretty far away from 0. So the way to do that is going to be like this. Right? Because then if you foiled that back out, the outer terms would be negative 18x and the inner would be negative x, so you get the negative 19x. The thing, if there's a way to catch that, it's just that the middle term's really far away from 0. So then you need that 9x to get like that extra boost to get farther away from 0. Like in my brain, that's basically what my inner monologue sounds like when I'm factoring a thing like that. So I guess that doesn't sound terribly mathematically rigorous, but it gets the job done, I suppose. And then the denominator, common factor of 8. And if we factor that out, we'll have 8 times x plus 9. All right, then second numerator, we're going to have, let's see, that's x plus 9 times x plus 7. All right, that one's not too bad to factor. But then in the denominator, all right, we've got to have a 3x and an x to get the 3x squared. Right, we know that part. And then what about the minus 10? Like, there are a bunch of different options, right? Like minus 5 and 2, 5 and minus 2. What order do you put them in? Is it 10 and minus 1, or minus 10 and 1? And where do you put them? For these sorts of problems, the first thing I would check is, would there be anything where there would be a factorization where you could cancel something? And if I look in the other numerator, there's an x minus 2, right? And 2 is a factor of 10. So I would try that first, and that actually works here. Because if you have a minus 2 there, and you have a plus 5 here, look at what you get. If you FOIL this out, outer terms, minus 6x, inner terms, plus 5x. That's minus 1x, or just minus x. So that actually works. And then it's time to cancel things, whatever we can. So those x minus 2s, we know we're getting them. Right? We're just talking about that. And then we can do the x plus 9s, but that's it. Right? Nothing else is going to cancel. All right, well, I guess we've got what we've got. So as a final answer, we're going to have 9x minus 1 times x plus 7 over 8 times 3x plus 5. And there is our answer. Again, not quite as clean as 7, 8, and 9, but it happens, right? They don't always work out the way you want them to. Speaking of things that don't work out the way you want them to, number 13. So if we were going to do what we've always done, which, well, always being the past 10 minutes, we're going to multiply by the reciprocal. So, all right, fine. X minus 4 over 2x plus 7 times 6 over x. Nothing factors, right? X minus 4 doesn't factor. Neither is 2x plus 7. Right? Everything is less than degree 2. So all those degree 1s that are in there, like the x minus 4 and the 2x plus 7 and the x, none of those have a common factor that you can pull out. So there's nothing to do. And there's also nothing that cancels. So what you would end up with here, and it's, I guess, accepted convention to put the monomial first. And I kind of wrote these other ones so it would just happen, like how the 8 shows up on the left of the 3x plus 5. But I would write this way, 6 times x minus 4 rather than x minus 4 times 6. It doesn't really matter, but I think it is more conventional to put the monomial first if you've got one. And then the bottom would be x times 2x plus 7. Like with the same sort of logic, I'd write it like that. And that is all you can do. So this one almost feels like it's wrong because we didn't cancel anything. And on these other problems, we've been canceling things out willy-nilly. But sometimes nothing works, right? And the problems in this section are kind of geared toward ones where you can cancel stuff, right? Because like that's the skill or one of the skills you're supposed to develop in this section, right? Is just kind of getting used to that thing and looking for it and looking to see where you can cancel. But it's certainly possible that nothing works. And I think there is a homework problem in this section where you'll get one where nothing works. It was worth bringing up for that reason, but also just because it can happen, right? Like you don't have to be able to cancel stuff. And I think that would cover all of the multiplication and division of rational expressions in section 5.1.